right, so today we're going to start chapter 5, okay, which is on two types of functions, exponential functions and logarithmic functions. Today we're just going to focus on exponential. Okay, first thing I want to just compare these two expressions, x squared and 2 to the x. Okay, in each expression you have a base and an exponent. Corey, what's my base in x squared? And my exponent? 2. Yeah, so the exponent is just what's up higher. And the base is what's below. Okay, the difference between these two is one has a base, or actually, let's focus on the exponent. One has an exponent that's an integer. The other one has an exponent that's a variable. Okay, when you start putting exponents in your variables, that's when you get exponential functions. Right? If you leave the exponent as a non-negative integer, that's a polynomial. X squared, x cubed, 1/2 x to the 5th. Okay, anything like that is a polynomial. Okay? When your variable is in the base and your exponent is a non-negative integer. But if the variable is in the exponent and the base is any positive real number except 1. Can't use 1, but it can be any other positive real number, like 2 to the x, that's fine. That's an exponential function. Okay, and I'm going to put up some examples in a little bit, things that are exponential functions and things that are not. Bless you. How come this wouldn't be considered an exponential function? What would happen if you raise 1 to a power? It would just remain the same forever. It would just be like a horizontal line, y equals 1. Okay? You've got to have a number other than 1. 2 to a power, that's going to grow very quickly. Okay? There's really two basic types of exponential functions. There's ones that go up very quickly, and then there's ones that go down very quickly. We'll talk about the names for both. Okay, does everybody have that? All right. So in an exponential function, the domain is -infinity to infinity. Okay? Think of this expression right here, 2 to the x. Ask yourself, is there any number you're not allowed to raise? Is there any number you're not allowed to use as an exponent on 2 to the x? No. You can do 2 to the 0. You can do 2 to the 1. You can do 2 to the -7th if you want. You can raise 2 to any power you want. So the domain is -infinity to infinity. Just remember, in this type of expression, the base can be any positive real number except 1. If it is 1, it's not that you can't graph it, it's not considered exponential. Bless you. Okay, these are all examples of exponential functions. Okay, 10 to the x, 4 to the v, pi to the x. Okay, so f of x, g of v, and h of x, these are all exponential functions. These are not. Okay. Under non-exponential functions, what is f of x? We just talked about the name of that. What is x cubed? Brett? Polynomial. That's a polynomial. Okay. A variable raised to a power, polynomial. DJ, how about g of x? Is that a polynomial?
No. Or yes. I don't think no, because you can divide it.
So if I rewrote it this way, which is the same thing,
Then,
yeah, that's a polynomial. Okay, anytime you take a power, you take a letter, raise it to a non-negative integer, you can multiply it by 1/2 if you want, that's fine. Okay, that's a polynomial. And y is kind of a mixture of a couple things. It's a radical function in the top and a polynomial on the bottom. Okay, but these are all non-exponential functions. Any questions on the difference between what is and what isn't exponential? Okay, so what makes something exponential? What are the two things you got to have? Yep.
The base has to be positive and greater than 1.
It's got to be positive in anything except 1. So it can be like 0.25. That's okay. So it's a base is positive, anything except 1. And what else? One other important thing. Yep.
The exponent is variable.
Exponent's got to be a variable. Good. Okay, let's look at the difference between these two. Okay, 2 to the x and 3 to the x. Which one of them do you think curves up faster? 3 to the x, yeah. Okay, especially once we get after 0. Okay, when x is greater than 0. I'm going to look at what happens when x is less than 0. We might see that behavior like we did yesterday with the roots. Things switch places. Let's graph 2 to the x, 3 to the x, and we'll start with zoom 6, and then we'll zoom in a little bit. Okay, so there's 2 to the x, and there's 3 to the x. All right, so let's zoom in. Let's just do a zoom in, see if that works. Zoom in right at the origin. Okay, so where does it look like these graphs switch places? Yeah, right at 0, 1. Okay, they switch places. All right, so 3 to the x is on top as long as you are after 0. If you go before 0, it's down below. Okay, if I were to graph y equals 4 to the x, if I was greater than 0, it would be above everything. But if I was less than 0, where would it be? It'd be below everything. So the higher your base, it kind of starts off a little slower, but then it picks up very quick, and then it'll stay above. Okay, so any questions looking at those graphs? All right, so let's look at this. Okay, we know anytime you have something raised to a negative 1, all you got to do is flip it, and we can make it positive. Okay. All right, so what I want to do is look at how we can rewrite something that has a base with a negative exponent. In general, we like to have positive exponents. Okay, it's not that we can't graph a negative exponent, but if we want to compare two things on paper without graphing them, we've got to have the exponent positive. Okay. What number is in front of x? A negative 1. Okay, so this is really a raised to the negative 1 times x. Okay, that's how you can think of it. And when would you end up multiplying two things together having to do with exponents? Anybody think of it like sometimes you add exponents if you had this. Here you do 3 plus 4 and get x to the 7th. But when would it come up that you would multiply these numbers? Not in this case, but something a little different. Yeah?
If there's like an exponent in parentheses and a right outside parentheses.
Yeah, if you have a power raised to another power. So what I'm going to do is think of this as a to the negative 1 raised to what power? The x. Okay, if I did a to the negative 1 to the x, that would mean multiplying negative 1 times x to get negative x. And the reason I did that is because I know how to simplify a to the negative 1. How do we rewrite a to the negative 1? 1 over a. Okay, so we get 1 over a raised to the x. So all we really ended up doing was taking the base, flipping it, and writing it with a positive exponent. So what if I had -3 to the x? Okay, what would that be the same as? Oh, sorry. That'd be a little hard to do. Let's make it, how about -x as my exponent? Let's try that. 3 to the -x. Yeah.
Would it be 1 over 3 to the x?
1 over 3 to the x. Yes. Okay, just following this pattern right here. Okay, any questions on that? All right. All right, let's graph each of these. Okay, 2 to the x, and now 2 to the -x. You get two ways you can do it. You can do what I just showed you to rewrite it, or if you're just graphing it, if that's the only thing you have to do, it's okay to type it in that way. Okay, it doesn't really matter. Okay, let's start with 2 to the x. And let's get a bigger picture. All right, so that's f of x. What is the domain of f of x? Yeah, all real numbers. It's going to go left forever. It doesn't look like it's heading to the right, but it is very slowly. You can plug anything you want in for x. -infinity to infinity. Now, what about the range? At this point, it's kind of a guess at how low it goes, but I think you can probably estimate what it's approaching, but it's not going to reach.
All right, numbers are greater than 0.
Yeah, so all real numbers greater than 0. 0 to infinity. Okay, we can confirm that. Just go to your table and watch what happens if you start typing in smaller and smaller numbers. Okay, oops, towards the negative side. Okay, so here we're getting a very, very small number, 0.00009, something like that, just in scientific notation. All right, so it is approaching 0, and if you go even more, eventually it might say 0, but it's because it ran out of decimals to round it off. Okay, at that point now we're like 0.0030 times and then a 1. So it's very close to 0. Yeah?
That's one of the big numbers with error.
The big number? It's too big. Too big for the calculator to do. That's why. You can't do 2 to the 5,000th power. Exponent is too high. Yeah, it's a good question though. You might think, is there a problem with it undefined? No, just it's too high to do. Right, and now let's look at 2 to the -x. All right, and if you just compare those two graphs, how does it look like they compare to each other? Flip over. Yeah, they look like they're flipped over the y-axis, and they are. Okay, we're going to look at that in a little bit. Okay, what's the domain of g of x? Yeah, it's going to go left and right forever. So it's all real numbers. And what about the range? Yeah, same range. So basically, whether you have a graph that's growing very quickly or coming down very quickly, it's really the same domain and range. Does anybody know what you call it when it's exponentially going down? We use a different word.
Exponential decay.
Yeah, with exponential growth, exponential decay. All right, so now looking at this in general, we're not just going to look at 2 to the x think about it in general, a to the x. What happens in this type of function, whether it's 2 to the x, 5 to the x, 12 to the x, doesn't matter. As x gets bigger and bigger, what happens to y? Yep, it also approaches infinity. Now, in this kind of function, what happens as x heads towards negative infinity? Y approaches 0. Okay, now we're going to look at it for g of x. Okay, that's when you have a fraction, like 1/2, 1/3, 1/5, something like that. As x gets bigger and bigger in g of x, what happens to y? It's approaching 0. And what happens in g of x as x gets more and more negative? It's a g of x approaches infinity. Okay, so it's the same behavior, it's just switched, depending if you're approaching infinity or negative infinity. Hey, any questions on that? All right. Does everybody have that? So the key difference here, whether you have a graph that's going to grow or decay, it's all about what the base is. Okay? If the base is more than 1, what do you think happens? Do you get growth or do you get decay? Growth. Take a number a little bigger than 1 and raise it to positive powers. It grows. Okay. Take a number that's between 0 and 1, like a decimal, and raise it to powers. Think of like 1/2 raised to the 5th power. That's half of a half of a half of a half. Or keep going. All right? It gets smaller. All right, so greater than 1, this is where you get growth, which we'll get into a little bit more. Between 0 and 1, that's decay. All right. Next thing I want to look at is I want to take f of x, and instead of having x, I want to replace x with negative x, and just see what happens. So in f of x, if I replace x with negative x, what would this become? If we replace x with negative x. Yeah?
Negative a to the x, or would it be a?
No, I'm not going to change the a. I'm going to leave that.
A to the negative x.
Yeah, it's just going to become a to the negative x. So if we replace f with negative x in that function, we get a to the negative x. And we just talked about how to rewrite a to the negative x. Right here. A to the negative x is the same as 1 over a to the x. Well, 1 over a to the x is really which other function? That's g of x. So if we take an f of x and change x to a negative, we get g of x. Okay. And the same thing happens in g of x. If you take and replace x with a negative, it turns it into f of x. So what that proves is these graphs are reflections of each other over the y-axis. We kind of saw it in the picture. This proves it. Right, so anytime you have a function, if you change your x to a negative and you get a different function, that's the mirror image of it over the y-axis. So that's an easy way if you want the mirror image of a function. Change all your x's to negatives. Okay, any question on that? So transformations with exponentials work exactly the same as they did with every other function we've learned. So I'm going to see if we can just get this without me going into too much detail. But the basic function is 3 to the x. I want to know what the plus 1, the times 2, and the minus 5 would do. Okay, what's the first number you would focus on here? Plus 1, the 2, or the minus 5? Brad?
Plus 1.
Yep, I'm going to focus on the plus 1. And what is the plus 1 going to do? Yeah, it's going to shift left 1. Anytime you have a function and you add or subtract something directly to the x, that's your left and right. Whether you do this, do something like this, that's going to shift whatever kind of function you're working with, left or right. In this case, left. Okay, next number we look at. DJ?
The 2.
Yep, I'm going to look at the 2. And what happens when you take a function and multiply by a number in front?
That's a vertical stretch.
Yep, that's your vertical stretch. By a factor of 2. And the last thing we're going to look at is the minus 5. Okay, what's the minus 5 going to do? Yep.
Horizontal shift down. I mean, vertical shift down 5.
Yeah,
I said horizontal.
it's okay if you just say shift down, as long as you give me the direction.
Okay.
So shifting down, and then how much? Down 5. Okay, so we had horizontal shift, we had vertical shift, vertical stretch. What's the only thing we didn't have?
Horizontal shift.
Horizontal stretch. Okay, and to do that, I'd have to stick a number in there. Okay, and the reason I didn't do that is because when you go inside the parentheses, everything is the opposite of what you would think. Okay, plus shifts left, minus shifts right. A bigger number actually compresses this. Right? A smaller number, like if I put in a 1/4 in front of the x, a smaller number makes it bigger. So inside the parentheses, all the horizontal stretching and shifting is the opposite of what you would think. Small numbers make it bigger, bigger numbers make it smaller. Outside, everything works perfect. Bigger number actually does stretch it bigger. A minus actually does shift down, plus would shift up. Okay. Yeah?
Is that, if there's a negative in front of the 2,
Mhm.
is that the same as still flip it?
That would flip it, yep. That would flip it vertically, so flip it over which axis?
Yeah.
It would flip it over the x. If I put a negative in here, it would flip it over the y. Yep. And that's actually what we just proved right here. Change your x to a negative x, it flips it over the y-axis.
Now that flip, would that be step number 3?
Which one? If there was a negative in front of the 2?
Yes.
Yep, so first thing is you still do the shift left, then you could do the vertical stretch, then I would say do the flip.
Okay.
Yep. That's fine. And we always do the vertical shift last. Okay, any other questions on that? All right, so that's it for the transformation. All right. Next thing, we got two functions, f of x and g of x. They look different, but they're not. These are the exact same thing. I think this is the preferred way to write it. To me, this is confusing. I look at this and I see a 2 as the base, and I'm thinking growth. Right? 2 is a number bigger than 1. It's going to go up. But it's not written the way it should be. So maybe once we rewrite it, we'll see that it actually isn't growth. Okay, so let's start with that. Okay, what's the first thing here that you notice just looking at the exponents? That's not the same. Kind of the way that it's written, not the actual numbers. But what do you notice about the way these exponents are written? Yeah?
Well, in the first one, the x is after everything. In the second one, the x is the first thing.
Yeah, we prefer the x to be first, not last. Okay? Just like when we do like square root functions. We write this. We don't normally write it like that. Okay? x always before your number. Right, so Andrew, can you rewrite that for me so x comes before the number?
2 to the negative 2x plus 3.
Good. 2 to the negative 2x plus 3. Okay, now at least I have the same order as g of x. All right, next thing. What number do I have in front of x right now that I don't have in g of x? I've got a negative 2. So what I'm going to do is factor that out and see what it leaves me with. Okay, if I factor a negative 2 out of x, what's left there? Just x. And Brad, if I factor a negative 2 out of the second part, what would I have left there?
Negative 1.5.
Yeah, it's negative 1.5. You can always check it by distributing. Negative 2x plus 3. Okay, now we're close. How can I somehow turn 2 to the negative 2 into 0.25? Think of a way you can rewrite 2 to the negative 2 without a negative exponent.
I know what the answer is, but I don't know.
Jenny?
1 over 2 to the second.
Yeah, anytime you got a negative exponent, flip it. So this 2 to the negative 2 is really 1 over 2 squared. And all of that is to the x minus 1.5. And DJ, what's 2 squared?
4.
4. And 1/4 is the same as
0.25.
0.25. Okay, so we showed that they are the same. Now, because I've rewritten it the correct way with the x first, I can very clearly see this is a decay function. My base is less than 1. And I've shifted the decay function to the right, 1.5 units. I can't really see that as easily by looking at it written this way. Okay. Questions on that? All right, this is kind of like its own separate little thing. It's going to tie into what we're going to be doing in the next section. But since we're talking about variables as our exponents, I'm going to show you this graph here. Okay, we're going to graph that. And what I'm interested in looking at is what happens when x gets really, really big. I don't care what's happening near the origin. When x gets really big, positive or negative direction. Let's see if we can look at it by hand. Okay. What happens to the fraction 1 over x when x gets really big? What does that fraction approach?
0.
It approaches 0. Okay. Does it ever reach 0? No. So we're taking something that's extremely small, and we're adding 1 to it. So we've got a number that's extremely close to what? 1. And we're going to raise it to a huge power. Well, if you take a number that's extremely close to 1 and raise it to a huge power, it's almost like there's like a battle between these two things going on. 1 to a power is just 1. So it's a number just a little bigger than 1. Extremely close. But the power is also extremely big. Okay, so let's graph it and see what happens. Okay, so we've got 1 plus 1 over x raised to the x. Now, technically, this is not an exponential function because the base is not a number. Okay. But we do have a variable that's an exponent, which is why we're going to look at it. Okay, so forget about what's happening near the origin. What does it look like is happening as x gets really, really big in the positive or negative direction? Yeah?
Kind of looks like it kind of levels itself out.
Yeah, it looks like it's leveling out and approaching something. And what do we call that when something gets very close to something?
A horizontal asymptote.
Yeah, there's a horizontal asymptote here. Okay, if you let x be 100, we get 2.70. If we let x be 500, we get 2.7156. If we let x be 5,000, it didn't go up that much. 2.715 to 2.718. Okay, let's check the negative direction. Negative 100, 2.73. Negative 5,000, 2.7186. Okay, so negative 5,000, it was 2.718. 6 if we round up, 2.7180. So we're very close to this number 2.718 something. Anybody ever seen that number before? 2.718? Okay, it actually is a special number. Okay, like pi.
Square root of pi?
Nope, it's not the square root of pi. It's e. Okay, there's a button for e on your calculator. And e is the number 2.718281828. It doesn't keep repeating 1828 after that. It changes. And it's a number that we don't use as much as pi. Okay? Where we're going to use it is when we talk about logarithms.
Does it end?
No, it's like pi. It just keeps going. I don't remember all the digits after that point, but it doesn't keep repeating 1828.
Do you remember how long was pi?
Pi, I remember a few of them.
How far?
3.14. 159, and a few more. So the number e, it's what we call the base on the natural logarithm. All right, so we're going to talk more about logarithms and specifically natural logarithms later on. And if I actually graph E on the screen, you'll see that it is a horizontal asymptote for that picture. Okay, it's just kind of an interesting function, probably not something you'd look at and be able to think of on your own, that it approaches the number E. But with a calculator, that helps us out a little bit. All right, so last thing we're going to look at is growth and decay. Okay. First thing is growth. Okay. Let's say we had a city with a population of P people, and it was increasing at a constant rate. Okay. Like the population is going up 5% every year. Okay. How many people do I have at the very beginning? What's the initial amount? Well, this case, it's starting at P. Yeah. So my population starts at P. It goes up 5% every year. Okay, after year one, and what we're going to assume here is this is a constant rate. The population just keeps growing. Obviously, populations can go up and down, but just keep it simple. In year one, I still have all the people I had. Plus, how would I figure out the increase? Let's say it went up 5%. We can just use an example. How do you find 5% of P? 0.05P. So you take your population plus your growth rate times your population. That's how you find the increase. Original amount plus your increase percentage times your original amount. It's always those three things. So in this case, if I don't want to use I don't want to use 0.05, I want to use R. What would this turn into? P plus RP or P plus PR? Okay, either way. And then what do these both have in common? P. So I can factor out a P from both. If I do that from the first one, I'm left with 1. And from the second one, I'm left with R. Now, what I put in the red box, that is my new population. Okay? That's going to now take the place of P. Right, so I just said before, it's your amount plus rate times amount. Okay. What's the amount of people that I'm going to start off with now in year 2? It's not P anymore, it's what? P times 1 plus R. Right? That's the amount of people I have now. So my amount of people is P 1 plus R plus, okay, what's my growth rate?
P times 5%.
Yeah, just in general.
So P times 1 plus R.
Yeah, so you could write it as your amount is P times 1 plus R, your rate is R, your amount, that's P times 1 plus R. This amount is always repeated at the beginning and the end. P times 1 plus R. Okay, now, what do both of these have in common? Yeah, they both have a P 1 plus R. So what I'm going to do is factor that out, just like I factored the P out up above. Okay, so here's my formula. My original amount equals, or a plus, my original amount times my growth rate. Okay, and if I factor out P1 plus R, well, I'd have P times 1 plus R on the outside. I'd be left with a 1 in the first spot, and I'd be left with an R in the second spot. Okay, what's 1 plus R times 1 plus R, if you write it the short way? Yeah, 1 plus R squared. Okay, so we get P times 1 plus R squared. Okay, and at this point, I want to just try to find a pattern to do this again. Okay, the first time we had think of this as to the first power, first year. Second power, second year. What do you think the formula for the third year would be? P times 1 plus R to the third. P times 1 plus R to the fourth. Okay, what about after T years?
P times 1 plus R. P.
Yeah, P times 1 plus R to the T, where T is how many years have gone by. Right? It's similar to the interest formula. Yeah. In the interest formula for compound interest, we have an n in here too. It's usually 1 plus R over n raised to the nt. But there's definitely some similarities with that. Yep, very good. Okay, and this is our exponential growth formula. Okay, P is your initial amount you start with. R is your rate, but you have to write it as a decimal. Okay, so be careful if you have like 2%. It's 0.02. And T is your time. Shannon?
What happens to the R in the second one?
Oh, in this part?
Yeah.
So when we factor out P times 1 plus R, this R is right there. Right? This 1 comes from when we factor out this entire thing. Do you see what I mean? It's like if you have like x plus 2x and you factor an x out, well, if you factor out the entire thing you have, you've got to put something there to hold its place. So we factored out the entire thing we had. That's where that 1 comes from. And then this part, the P1 plus R, that's what's in the red box. That's what we factored out. Okay, so that's our formula for exponential growth. Okay, exponential decay, I'm not going to go through the whole process again, but basically just change plus to a minus. All the letters mean the same things. All right, so we're going to look at an example where we have a town of 50,000 people. Population's going up at 2.5% per year. First, I want to model this with a function. And then basically I want to know when the population is going to double. How many years will it take to double? All right, so let's start with our formula. Okay, population as a function of time. Anybody think they can give me my equation based on the data we have? So you're going to use your exponential growth formula. Brad? 50,000, yep. Good. Okay, some people forget to change that to a decimal. You have to change your percent to a decimal. He did it perfect. 0.025. Okay, if we can simplify that, we will in a second. And anything else? T is the exponent. Okay, there's your model for the function. Okay, the only thing I'm going to do is combine some like terms. What's 1 plus 0.025? 1.025. Now you should be able to see that this is growth. How can you tell just by looking at this problem that it's growth and not decay? Just even if I didn't give you the word problem, I just said, look at this. Growth or decay? Right, one word. Yep. And the base is bigger than 1. It's not that much bigger than 1, so it's not going to go up quickly. It's going to go up very slowly. All right. Now for the next part, the problem with trying to solve this is by hand is we have a variable in the exponent. In this class, I haven't taught you how to deal with variables in the exponent yet. It's very easy. It's not hard. But it's not the way you can do it in Algebra 1. Okay? So we're going to hold off on doing it by hand. So how could I do this on the calculator? I want to know when this reaches what number? 100,000. Okay, you might be able to do the first step by hand, which is divide by 50,000. But from there, then you'd be stuck with this variable as the exponent. All right, so how can I do this on my calculator? Yeah?
For 1, do 50,000 times 1.25 raised to the x.
Right, so fix that. 50,000 times 1.025 to the x. Yep.
And then y to
100,000.
100,000.
Anything else I should do before I hit graph?
Your window.
Yeah, I should adjust my window. I at least got to go to 100,000. I like to go a little bit more. Let's go like 101,000. 100. Yeah, 101.
Why'd you put parentheses on?
I'm sorry. All right, and let's see. We don't have to worry about negative population. Population can't go any lower than 0. X max, that's how many years it's going to take. Well, let's assume it happens within 45 years. If it doesn't, we'll adjust it. Oh, I have a random box there. Thank you. Okay, so that's our population going up. Maybe I should have set my Y max a little higher, but I think it's on the screen enough we can get it. And now I got to calculate what? The intersect. Intersect. It's going to take about 28.07 years. To reach 100,000 people. Okay, in probably next academic week, we're going to come back and do the same problem again, except I'm going to show you how to solve it by hand. What's that?
So calculator's easy.
It's pretty easy to solve by hand too. I mean, it's kind of equivalent to Algebra 1 if I said, we're going to solve this on the calculator, and then next week I'll show you how to solve it by hand. Well, it's really not that hard to solve by hand. It's a couple steps, but it's not that challenging. All right? So that's our time. Okay, so be careful when you graph, okay, as always. Make sure your x and y axis make sense. Okay, negative people doesn't make sense. Negative years, that doesn't really make sense either. Okay, for our models that we're writing, we're assuming that the model predicts the population from this point forward. We can't assume that the model can go back in time and predict what the population used to be, because we don't know if it was always growing at 2.5%. Maybe things just started growing now, right? We don't know. Question? Right, it's like another kind of problem where things grow, but it's a specific kind of growth, doubling. All right, so we're going to start with 100 bacteria. It's going to double every hour.
Wait, a question before we start.
Yeah.
Does this simulate those acid questions where you're going to have to do it on a test too?
It's not like a mixture problem at all, no.
Well, no, but like, is it going to be on the test? Like, the question just like this, but with different numbers?
Oh, like the mixtures one?
Yeah.
Yeah, I'll probably ask you something about doubling. I'll ask you about a population increasing, something doubling. There's like 3 types. So if I don't know if I can fit them all in the test because I don't want it to take super long. But I'm going to ask you at least 2 out of the 3 types. Okay, how many bacteria do we have at the start? 100. Okay, after an hour, how many? 200. And I'm just going to write 200 using the original amount and 2, right? Just so you can see a pattern here. How about after 2 hours? 400. After 2 hours, 3 hours, we got 800. Okay, look at the pattern. Original amount times 2 to the first power. Original amount times 2 to the second. Original amount times 2 to the third. So what do you think after t hours? 100 times 2 to the t. Right? And that's basically how we figure out our formula for something doubling. It's one original amount times 2 to the t. Okay? Initial amount times 2 to the t, and we have to divide that by the length of the time to double. Okay? In this case, length of time to double was 1 hour. Okay? And I'll show you why we need to do that on the next type of problem. So if you look at this, it's really just the formula we had before. There's an initial amount, except before we had 1 plus r to the t. Well, if something's doubling, what percent increase is that? Think about that. If something's doubling, what's the percent increase? Not 200, that'd be tripling. 200 would be that'd be in between. 100. Okay, if you have a 100% increase, that's doubling. So if you had a score of 50, and I said to increase it by 100%, you take your original amount plus your original amount times your rate of increase. And what's 100% as a decimal? 1. So if something doubles, it's a 100% increase. So all we're really doing in our previous formula is changing r to a 1. That's where the 2 comes from. So if you wanted to do something tripling, what would this number become? Become a 3. Okay? Because that'd be a 200% increase. Something triples, it's a 200% increase. 2 plus 1. That's where the 3 would come from. Okay, but we're just going to look at doubling. Right, so if we had 100 bacteria, it's going to double every hour. I want to know when we hit 350,000. Okay, how many people think that'll take a pretty long time to go from 100 to 350,000?
An hour.
Well, in an hour you'll have 200, but
Oh, yeah.
Because it doubles if it doubled every minute, yeah, we'd be in trouble.
It'll probably take like 12.
Probably within a day.
12, 24 hours.
Yeah, it's probably going to be within a day because doubling goes up very quickly. Exponential functions are the fastest growing functions. Okay, they go up very, very fast. Right. So what's my formula for this one? Let's write our amount as a function of time. Can you start me off, Heaven? What's my initial amount? Yep, 100. And then that's times what? Yep, 2 to the what's the exponent on 2? Yeah, just t. And in this case, we'd have to divide by the length of the time to double, but it's happening every 1 hour. So length of time to double is 1. Okay, so it's just t over 1. Right, and now we want to know when that amount hits 350,000. This is just like the population problem. Put 350,000 on the left. Put the other expression on the right. And let's see where they cross. Okay, so I got 350,000. And I got 100 times 2 to the x. Right, this time for my window, I think it's going to happen within a day, so I'm only going to go to 24 hours. And let's set our y max 400,000. There's the amount of bacteria. And there's where it hits 350,000. So it's going to take about 11.77 hours. Don't worry about converting that to hours and minutes. That's just a little over 11 3/4 hours. So 3/4 of an hour is 45 minutes. So it's a little over 11 hours and 45 minutes. Okay, but that's fine. Okay, any question on that one? All right, last one. Okay, so the opposite of something doubling, it's called half-life. Okay, does anybody know where that term is used? In chemistry? Yeah, you might use it when you talk about like a radioactive substance. And basically what the half-life is the amount of time for half of the material you have to break down and disappear. So let's say this was radioactive material. And let's say every hour, half of it disappeared. Okay, so if I started with this amount, after 1 hour, that's what I have left. Okay, after another hour, I have half of that left. Okay, and after another hour, I only have half of that left. So each hour that goes by, the amount of material goes down by half. Okay, and this, in terms of like radioactive material, can be kind of a bad thing. Because if you have radioactive material that has half-lives of thousands of years, so let's say you had 2 million tons of nuclear waste, and the half-life was 1,000 years. It's going to take 1,000 years for 2 million tons to go down to 1 million tons. This is going to take a very long time. Some substances have really fast half-lives. Okay, they can have half-lives in like the millisecond range. So it's almost like the second the substance is created, it's almost destroyed. Okay, carbon is another substance that has a pretty long half-life, and they use it for what's called carbon dating. They can figure out how much carbon is left in the object they're trying to date, and based on that, figure out the age of the object. Right, so your formula for half-life is very similar to doubling. It's just we have 50%. Think of it as 1 minus 0.5. Your rate is a 50%. So this is a decay. So take your initial amount times 1/2 to the t divided by the length of the half-life. Okay, and here I'm going to show you why this division is important, because I'm not going to let it be 1 this time. Okay, this time I've got a half-life, a substance that has a half-life of 20 days. Okay, that means every 20 days, half of it disappears. I start out with 5 grams. First thing I want to do is write an equation that represents my amount as a function of time. And then I want to know, when will I have under a gram remaining? Okay. Maybe this is a dangerous substance, but once we have less than a gram of it, it's not harmful anymore. So maybe we're trying to figure out how many days before it's not harmful. So let's start with our equation. Somebody give me my equation that'll give me the amount as a function of time. Yeah.
So 5 times 1/2 t. Or would t be 20? Or is it just wrong? I think it's wrong, I guess.
DJ?
That would be t divided by 20.
Would be t divided by 20. Basically, this entire exponent represents the number of half-lives you've gone through. After 20 days, 20 divided by 20 is how much? 1. Okay, after 20 days, you've done 1 half-life. Okay. What's 40 divided by 20? 2. So after 40 days, you will have completed 2 half-lives, or 2 half-lives is equivalent to how much material left? A quarter of it. Okay. After 60 days, you will have done 3 half-lives. Half, half, half. Now you have 1/8 of your material. Right? That's why you need to put in this divide by 20. Right? Now I want to know, when is there less than a gram remaining? All right. Well, let's graph 1, okay, in y2. Put in 5 times 0.5 to the x over 20. Let's do a standard window. Not exactly what we wanted. Okay, let's set the x to 0. Okay, don't worry about negative amounts. Lowest amount you can have is 0. And let's set x a little higher. Let's try 50 days. Okay, so there's our substance decaying. And I think we just barely have it. So do our intersect. It's going to take about just over 46 days. Okay, 46.4 days. And it says, when will there be less than? So I could say any time, technically any time after 46.4 days. Okay. Any question on that? Will the amount of material I have ever reach 0? No. That's the problem with radioactive stuff. It never really completely goes away. It'll get smaller and smaller and smaller, but there's always a little bit left. Same idea with medications. Okay? A lot of times when you take a medication, it has a half-life. So there's always a little bit of medication left in your system at a certain point. Right? And there's actually a lot of neat problems you can do related to like pharmacy, if you're interested in that kind of stuff with half-life. All right, so the homework, it's on 268. Okay, and it's quite a bit of graphing, so you will need your calculator. It's 4 through 7, 11, 13, 15, 16, 19, 25, 27, 29, 31, 35, 47 to 49, and 57.